So welcome back to the discussion on approximation methods in quantum mechanics. So today we are going to discuss the last approximation method in our syllabus, which is called the variation method. Okay, so we have discussed many approximation methods in quantum mechanics. Particularly, I have discussed the Brigade approximation, and you might have learned the time-independent perturbation theory. And this is the last approximation methods that we have to study according to our syllabus. Okay. So we can just go through what is the variation method, and we will illustrate it using one problem. So that will be today's lecture. Okay. Now the variation method is mainly used to find the approximate value of the ground state energy or the excited state energy of a system. Okay. Suppose you know a system. Okay. So consider you know a system with the Hamiltonian x, and suppose this Hamiltonian x is not exactly solvable. Okay, so then we cannot find the exact energy eigenstate of the system. Okay, so suppose x is not exactly solvable, then we can use this variation method to find the approximate value of the energy eigenstate, maybe the ground state energy or the first excited state energy, second excited state energy, and so on. Then the variation method can be used to get an estimate of, because we will not get the exact value, so an estimate of energy eigenstates. Or more correctly, we can say that we get the upper bound of energy state. We get upper bound of energy eigenstates. Now the main use of this variation method is to find the upper bound of ground state. So although we can find all energy eigenstate or the upper bound of all energy eigenstate, but it is mainly applicable, or it is mainly used to find ground state. Okay, now we can see how we can find the ground state energy of a Hamiltonian x, which is not exactly solvable. Okay, so the method is, so first we assume a trial wave function. Okay, so in order to find the ground state energy, okay, so better I will put EGS, ground state energy. So in order to find the ground state energy, so first we assume a trial wave function. So this trial wave function is psi 0. Okay, so get psi 0. Now obviously the psi 0 will have certain parameters to it, and the parameters, and putting the parameters, will be function of some parameters alpha 1, alpha 2, etc. some alpha L. Okay, so there will be many parameters for this wave function or trial wave function. So this is basically a guess, it is a wild guess. So we will guess a trial wave function. Okay, now we can find, also we assume this trial wave function is a normalized. Okay, so we assume a trial wave function is normalized. That means its norm is 1. Then what about its expectation value of the Hamiltonian The expectation value of the Hamiltonian I can write as psi 0 h psi 0. Now this expectation value would be always greater or equal to the ground state energy. Okay, so ground state energy would be always lesser or equal to psi 0 x psi 0. So psi 0 is just some trial wave function. Okay, so it is not a ground state wave function. So obviously, if you find the expectation value of Hamiltonian in this psi 0 trial wave function, then we'll get energy. Either it would be equal to the ground state energy or greater than the ground state energy. Okay, so if psi 0, what the wave function that we have guessed is exactly the ground state wave function, that is also possible. Sometimes our guess becomes true. Okay, so if psi 0 is exactly the ground state wave function, then we'll get the exact ground state. Otherwise, the exact ground state energy. Otherwise, the expectation value of the Hamiltonian in the psi 0 state would be greater than the ground state energy. Okay, so its proof is very simple. Okay, so what is the proof? So proof we can complete within few steps. So the psi 0 is a trial wave function. Now psi 0, it is possible to explain psi 0 in terms of energized state. Okay, so suppose get phi n, maybe the set phi n are the energy eigenstates of H, then this set phi n can be considered as a complete set, so that it can expand any vector in terms of this complete set. Okay, that is from the completeness property. So then we get psi 0, it is possible to expand it some m equal to some 0 to infinity. Okay, maybe some n-dimensional vector space. Okay, consider this n-dimensional vector space and Cm get phi. Okay, so that's about your get 0. Phi m are the energy eigenstates. So that is the Hamiltonian acting on phi m will give Em phi. Okay. Then we can find the expectation value of H in terms of psi 0. So psi 0 H psi 0, that would be equal to psi 0 is sum over m and sum over k phi m Cm H Ck phi. Okay, the Cm and Ck can be taken outside, so sum over m comma k, Cm star Ck phi m H phi. So how we are writing this? Because we know that get psi 0 is sum over m 0 to n Cm phi. Okay, so that is why I have written this. Okay. Now this H acting on phi k would give the energy eigenstate, phi k is energy eigenstate, so that what this would give Ek into phi k, and Ek is energy eigenvalue can be taken outside from that inner product. So this will be sum over mk Cm star Ck, and you will get Ek linear product phi m phi. Okay, now this phi m phi k, okay, since we assume this the eigenstates are the normalized or the orthonormal set, so then this inner product would become the canonical vector. So we get sum over mk Cm star Ck Ek, the canonical delta mk, and if we sum it over k, what would be the final result? It would be sum over m mod Cm square d. So if you sum it over k, then you have to replace all k with m and remove this counter data function, and sum over k is over here. So there is only remaining is sum over m. Okay. Now which would be the ground state? The ground state would be E0. E0 is a ground state, and E1 would be the first sector state, and so on. Okay. So that would be, I can write is equal to modulus of E0 square into the ground state, which is EGS, plus sum over m equal to 1 to n mod Cm square E. And what is the left hand side? The left hand side is psi 0 x psi 0, which is of this quantity. Now obviously this quantity would be greater or equal to EGS. Okay, EGS is only this number, and we have many other terms here. Okay, so obviously this would be always greater or equal to EGS. Or, so that is our statement. The first statement is the variation principle, that is psi 0 x psi 0 is always greater than or equal to EGS. Okay, so that means if you minimize psi 0 x psi 0, if you minimize psi 0 x psi 0, then you will get a value which will be very close to EGS. So that is the idea of the variation principle. Okay, now we have to minimize the psi 0 x psi 0 to get a value very close to the ground state energy, and sometimes it will be exactly equal to the ground state energy. Okay, so what is our next procedure? So we have to minimize the expectation value of x. Okay, now how will you minimize it? So psi 0, so remember psi 0 has many parameters, alpha 1, alpha 2, etc. Okay, so then we can minimize the expectation value of the Hamiltonian with these parameters. That is, to which parameter value the Hamiltonian minimizes. So we will set, so dou by dou alpha 1 of psi 0 x psi 0 equal to 0. So dou by alpha 1, dou by dou alpha 2, dou by dou alpha 3, and we will find to which all parameter values of alpha 1, alpha 2, alpha 3, etc. Okay, in general I can write some alpha L, dou by dou alpha L of psi 0 x psi 0 equal to 0. Then by setting this we can find the parameter which minimizes the Hamiltonian. Okay, so the parameter which minimize the Hamiltonian I can write alpha 1 0, alpha 2 0, etc. up to alpha n 0. Suppose this is the set of parameters which minimize the Hamiltonian. Then I can directly find h minimum. Okay, so from this I will get psi 0 h psi 0 minimum. So this psi 0 h psi 0 minimum, this value will be very close to the ground state energy. Okay, so I can write slightly greater than or equal to EGS, but this value would be very close to EGS. It's approximately equal to EGS. Okay, so this h minimum, so by write psi 0 x psi 0 minimum gives upper bound for EGS. So this is variation method. Okay, so I can just summarize what are the things that we have discussed. Okay, suppose we have a Hamiltonian x which is not solvable. Then assume a tried wave function. Just guess a tried wave function. So this guess would depending upon your experience. So from our experience, we can guess some trial wave function. Now I can say that obviously the expression of Hamiltonian in this trial wave function would be greater or equal to the ground state energy. So we can straight away I can say that the psi 0 would be always greater than or equal to EJS, and that I have already proved. So this is a proof that I have done. Okay, then if you minimize this expectation value, and how will you minimize it? Because this trial wave function obviously depending upon certain parameters. There will be certain parameters on this trial wave function. I have just put the trial wave functions are alpha 1, alpha 2, alpha 3, etc. Okay, then we have to find the parameters, the parameter value of the wave function in such a way that we minimize this expectation value. Okay, so minimize psi 0, which is psi 0, and this would be very close to or greater EGs. So we will get the upper value or the energy value very close to the ground state energy. Okay. So that is why we say that from the variation method we can get the upper limit of ground state energy. Now the next question is it possible to apply the same method to find the higher energy states? That is also possible. You can find the first excited state energy, the second excited state energy, and so on. So how we will do that? So now we have just described how to find the upper bound for the ground state. So next we will see how to find the upper bound for the first excited state. Using variation method. Okay, so in order to find the ground state, again first part what we have done is we have assumed a wave function. We assume a trial wave function. So similarly here also we will assume a trial wave function. So that is you guess a trial wave function. Trial wave function I can put as psi 1. Consider a trial wave function psi 1, which is orthogonal to psi 0. So remember psi 0 is the trial wave function which is that we have used to find the upper bound for the ground state energy, and we got the upper bound for the ground state energy. Now then thereafter what we can do is we can assume another state psi 1, another trial wave function psi 1, which is orthogonal to psi 0. So that is psi 1, psi 0 must be 0. Okay, so then what will be the expectation value of Hamiltonian in psi 1? That would be obviously greater or equal to the energy of the first excited state. Okay, so that is the idea. So if you can able to guess a trial wave function which is orthogonal to psi 0, which the trial wave function is used to find the upper bound of the ground state energy, then the expectation value of the Hamiltonian in psi 1, that would be always greater or equal to the energy of the first excited state. Okay, so this you can prove it. Okay, so that I am leaving to you, that is to prove this statement if this condition is valid. Okay, now I can minimize this expectation value. So if you minimize this expectation value, we will get the upper bound for the first excited state. Okay, so the psi 1 H psi 1 would be approximately equal, or minimum would be approximately equal or greater than the first excited state. So it will be very close to the first energy of the first excited state if you minimize it. And how to minimize that we have already discussed when you are calculating the ground state. Okay, so that is the variation method. Now we can summarize this entire step using, we can say that the algorithm of variation method. We can summarize what we have discussed till now. Okay, so the algorithm, first we can discuss what is the algorithm to find the upper bound of ground state energy. This is how to find the upper bound of the ground state energy. Okay, so what is the steps? What are the steps? The step 1, guess and normalize the normalized tri-wave function psi 0. Now if it is not normalized also, that is not much issue. You can normalize it, you can always normalize it by taking the mod square of integration must be equal to 1. So from that information you can normalize any unnormalized wave function. So that is not a big issue whether you have a normalized wave function or a non-normalized wave function, that doesn't matter at all. So that we can always do, you can just divide it with the norm square. Okay, so that is we can do it. Okay, so guess a normalized wave function psi 0. Now this psi 0 must be a function of some parameters. Okay, this alpha 1, alpha 2, etc., alpha L are the parameters. Okay, so then the second step is, what is the second step? The second step is we will find the expectation value of Hamiltonian in terms of psi 0. Okay, so this would be always greater than or equal to the ground state energy. Okay, now minimize. So minimize the expectation value of Hamiltonian and find. So we have to find the parameters which minimize the Hamiltonian, the parameter value, and find the value of parameters, and that we can denote by symbol alpha 1 0, alpha 2 0, etc. to alpha L 0. Now how will you minimize it? So dou by dou alpha L, the expectation psi 0, h psi 0, that will be 0 for alpha L 0. Okay, so from that we can find out which is the parameter value which minimizes the Hamiltonian. Okay, now the third step. So what is the third step? So from that we can find the lower limit of this expectation value. Okay, so then the fourth step is this psi 0, h psi 0 minima. Either it would be approximately equal or slightly greater than the ground state energy. So with this we will find the upper bound for the ground state energy. Okay, so the ground state energy, either this value, this minimum value of this Hamiltonian, either it will be equal to ground state energy or slightly greater than the ground state energy. Okay, now how to find the excited state, the upper bound for the excited state? So that we have discussed here. Okay, so in order to find the excited state, okay, I can write this. I can write 4. It is just the tri-wave function psi 1, which is orthogonal to psi 0. Then thereafter what we will do? Orthogonal to psi 0. Then what we can write is this psi 1, psi 0, and thereafter repeat step 20. It's 20. Then we will get the upper bound for the first excess state. Now similarly, you can go for the second excess state energy, the third excess state energy, and so on. So that's about the variation method. So this is the simplest approximation method which is available in quantum mechanics. And sometimes it is very powerful depending upon our experience. Okay, and suppose you have worked out for certain molecules, and if there is a slight change in the bonding of the molecules, then we can guess the wave function of the earlier molecule as a trial wave function, and then we can use that information to find the ground state energy of the new molecule. Okay, so that is the idea behind it, and that is the application in the chemistry as well. We can find the energy level, the approximate energy level of a molecule. Finally, we can have an illustration on the variation method. So we have a simple problem here. So find the upper limit of the ground state energy of one-dimension harmonic oscillator using variation method. And the question itself, it is said that you can use a trial wave function is of the form psi of x is equal to a into e raised to minus bx square. Okay, so this is a Gaussian wave function, the Gaussian function, and there are two parameters here, capital A and small b are two parameters. But we are not sure whether it is normalized or not, so better we can normalize it first. Okay, and we can see what would be the exact form of the wave function if you normalize it. Okay, now first of all, if you take a one-dimensional harmonic oscillator, what is the Hamiltonian for it? So the Hamiltonian I can write minus h bar square by 2m d square by dx square plus the potential half m omega square x square. So this is the form of Hamiltonian. Now we have to find the upper bound of ground state energy of this particular Hamiltonian, and actually we have solved it earlier itself. We have exactly solved the energy states of this harmonic oscillator problem. Okay, and that is why we have picked this example. That is, if you use the variation method, is it possible to get the exact result or not? Okay. Now, first we can normalize this wave function. Now, if you look at the harmonic oscillator problem, the potential V of x is a quadratic function of x, and here x can go from minus infinity to plus infinity. So therefore, obviously, if you integrate mod psi of x square dx from minus infinity to plus infinity, you should get 1. Okay. So what is your wave function that we have assumed? It's a into e raised to minus bx square. So therefore, we should mod a square integrate from minus infinity to plus infinity e raised to minus 2bx square dx must be equal to 1. Now this is a Gaussian integration, and its result is well known. Okay, you can remember this formula: minus infinity plus infinity e raised to minus ax square dx equal to root 5 by 8. You can remember this formula. So if you remember this formula, then what will you get? Mod a square in the root of 5 by 2b equal to 1. Then what would be a? So this implies that a would be equal to 2b by 5 all raised to 1 by 4. Okay, so if you normalize your trial wave function, the a is in terms of b. I can write a equal to b by 5 all raised to 1 by 4. So therefore, your trial wave function psi of x is 2b by 5 all raised to 1 by 4 raised to minus bx square. So therefore, we have only one parameter now. The parameter is b. There is no a. Okay, so a I have written in terms of b after normalizing the wave function. Okay, so next is we can find the expression of Hamiltonian in terms of this wave function. So we can find the expression of the Hamiltonian. So that would be minus infinity to plus infinity psi star of x psi of x dx. Okay. Now it is a real new function, so psi star will be same as this. So psi star inside there will be 2b by pi all raised to 1 by 4. So I can take 2b by pi all raised to 1 by 2 commonly outside into integral minus infinity e raised to minus dx square minus h bar square by 2m d square by dx square plus half m omega square x square e raised to minus dx square dx. Okay, now I can split this into two integrations. One is the term containing minus h bar square by 2m d square by dx square. The second integration would be the term containing half m omega square x square into this term. Okay, now what would be d square by dx square? The second derivative of a raised to minus dx square. So first we can find the first derivative d by dx of a raised to minus dx square. So if you differentiate it, you will get a raised to minus dx square into minus 2bx. Okay, so if you differentiate minus dx square, you will get minus 2bx. If you differentiate it again, d square by dx square of e raised to minus dx square, what will you get? It will be derivative of this quantity, and here we have used the product rule. So we will get e raised to minus dx square again, then minus 2dx square plus e raised to minus dx square minus 2. So second derivative of e raised to minus dx square has two terms. So therefore, if you expand this integration, you will get three integration terms. So what are they? This 2b by pi all raised to 1 by 2 can be taken commonly outside. So the first term would be minus h bar square by 2m integral from minus infinity to plus infinity. This term I can write, that would be minus 2bx into e raised to minus 2bx square. Sorry, this minus 2bx whole square, so that will become plus 4bx square. Sorry, so 4bx square e raised to minus 2bx square dx, that will be the first term, plus then the second term will be minus h bar square by 2m integral from minus infinity to plus infinity minus 2b minus e raised to minus 2b x square dx, and the third term will be plus half omega square integral from minus infinity to plus infinity e raised to minus 2bx square x square dx. So we have to perform this kind of integration. So here 4b is a constant, can be taken outside. So there will be x square minus 2bx square dx term here. Here there will be e raised to minus 2bx square term, and again e raised to minus 2bx square x square term. So we have to perform this integration, and we will be using these results in our integration to find the expectation value of Hamiltonian. The first one is we already discussed, is nothing but the integration of a Gaussian function is a well-known thing that I have discussed when we find the normalization of the normalization constant of the big function. And second integration is again a simple thing. The second, if you look at second integration, it is an even function. So if you write the integration from minus infinity plus infinity, can be written as 2 times of integral from 0 to infinity of this. Okay, now it is possible to write this integration as a gamma function or gamma integration, and from that we get this result. Okay, so you have to recall that the gamma integration is from 0 to infinity from t raised to n e raised to minus t dt is gamma of n plus 1. Okay, so we can use this result. Okay, so for that I have to convert this integral form into this particular form, and that is possible. What you can do is you can just put 2bx square as t. If you put 2bx square as t, then it is possible to rewrite this complete expression in this particular form. And I can identify what is your n. From that, we will get the result of that integration. Okay, so that is a step, and this step you can do yourself, and I am giving it as an homework for you. Okay, so then what would be our Hamiltonian? Okay, so if you look at the Hamiltonian, that would be b by pi all raised to 1 by 2, then minus h bar square by 2m for b square. Then we get this integration, minus x square e raised to minus 2bx square dx, and that is nothing but 1 by 4b times root pi by 2b, then plus or minus h bar square by 2m. Then there will be a minus 2b outside of the integration, and the next integration is this integration, and that will give root pi by 2b, then plus half m omega square. The next integration is this one, and that will give 1 by 4b root pi by 2b. And if you look at this expression, this root pi by 2b is commonly present in all three terms, and outside there is a 2b by pi all raised to 1 by 2, and that would cancel. Okay, and certain other terms, for example, this 4 would cancel, a d square, a d will cancel here, and minus into minus this will become plus, and 2b by and 2b would remain there, and this would become minus h bar square by 2m times b minus or minus plus h bar square by 2m times 2b, okay, plus m omega square divided by 80. So if you add these two, you will get plus h bar square by 2m into p. So this would give h bar square b by 2m plus m omega square divided by 8. So this would be your expectation value of the Hamiltonian. Okay, in the trivial function. Now we have to minimize this expectation value. Okay, so how will you minimize it? So I will find the derivative of the Hamiltonian in terms of the parameter. Okay, so we will set the d by dv of the Hamiltonian will be 0 and b equal to b0. Okay, so if you find the derivative with respect to b, what will you get? H bar square by 2m plus m omega square by 8. If you differentiate 1 by b, you will get minus 1 by b square, and you have to put b equal to b0, or what do you get? M omega square by 8 b0 square equal h bar square by 2m, or b0 square. B0 square can be written as 2m square omega square divided by 8 h bar square. Then what would be your B0? So this 4. So finally, you will get the parameter which minimizes the Hamiltonian. The parameter B which minimizes the Hamiltonian will be m omega by 2. Then what would be the minimum Hamiltonian? H minimum. Just put the value of B0 here. Okay, so that would be h bar square by 2m, m omega by 2h cross plus m omega square divided by 8 the m omega 2h cross. Okay, so one m would cancel, one h cross would cancel, you get m omega, h cross omega by 4 plus 1 omega, 1 m would cancel, 1 h cross omega by 4, and that is exactly equal to h cross omega by 2 is the exact value of the ground state energy of harmonic oscillator. So we are getting the exact value of the ground state energy eigenvalue for the harmonic oscillator. That is remarkable. Now there is not really a surprise to us, because we have to think the wave function, the tribe wave function that we have assumed is a Gaussian function, and which is the exact the ground state wave function of the harmonic oscillator, and that is why we are getting the exact ground state. So sometimes it happens that the tribe wave function matches with the exact the ground state wave function. Then the energy would also matches if you minimize it. Okay, so this is the simple illustration of the power of the variation principle. Okay, so if you are able to guess the proper the tribe wave function, then we will get the upper limit of ground state energy that would be very close to the exact ground state energy. Okay, so thank you all for your patience. So with this we have completed the discussion on the approximation methods in quantum mechanics. Thank you.